So if you drew this graph here, right, y equals 2x, well, it's assuming you chose this as your scale, something like that, right? If you want the area underneath there, from x equals 1 to x equals 4, so you want from here to here, right? So you want this area underneath the curve. So we're talking about between the curve and the x-axis. So if you want that area right there. The fact that this is a straight line means you can use just geometry to find it. And of course, when you first learn about area when you're a little kid, you count squares, right? That's what area is, how many little squares are in there. And you count squares and you probably get how many here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what do we got here? These two together is 13. And those two together is 14, is that right? And that's 15? 15. Of course, if you want to do it another way, what you can do is the area of a... You could do it a couple different ways. Any ideas here? Any suggestions? The whole thing minus the white part. This is one way, right? So the area, and this is important sort of for what we're going to do, right? You could do the area up to here minus the area up to here, right? The whole thing, take away this little thing. So I'm going to put big triangle minus little triangle. If you were actually doing that, you would have the big triangle is, what is it? It's 4 times 8 divided by 2, right? Move that over there. So we'd have, what do we have? 4 times 8 divided by 2 minus, the little triangle is 1 times 2 divided by 2, 1, right? So we got 16 minus 1 is 15, right? What's another way we could do it? I mean, that's going to be a good way for what we do later on. Another way is just to remind you of what shape is this blue area there? It's a trapezoid, right? It's actually a trapezoid. You probably think of a trapezoid from when you're in elementary school and you think of this kind of trapezoid, right? A trapezoid can be straight on one end. It can have different angles on each end. All of those are trapezoids. It just means that these have to be parallel, one set of parallel sides. So it's good to know how to find the area of a trapezoid. The area of a trapezoid, you may remember a formula for that. Basically what it is it's the average of the two heights, the height on either side here. If you averaged out the height, it would look like this, right? If you add the two heights, or bases, or whatever you want to call them, if you add the two sides there, the area of that trapezoid is going to be 2 plus 8. 2 plus 8 divided by 2. That's the average height times the width of that interval, right? Times the width of that thing. So the average height times the width is 3. Average height in this case. I'm calling it height because it's on its side. If it was the other way, you could call it something else. But that's important to realize how to find the area of a trapezoid for what we're going to do. The width of the thing times the average of the two heights, right? One side, the other side, divide by 2. Does that make sense? So you got 5 times 3, 15. Okay? That's the same thing there. I don't want to dwell on the area of things that you already know, but I would like you to do the same thing, but now when we have this bizarre function here, maybe we can cheat a bit and just make a table to use. What do we got about? Well, yeah, I paused it for a long time there, but we're counting squares. Here's the graph. There's the values for that thing. Counting squares, what do we have? 30 plus maybe 31, 32, 33, somewhere about that. Really roughly 33. Those of you who are skipping ahead here, 33 and something. 33.6 maybe. This is I made the table of values, see previous page, right? Or take your lasso tool and move your table of values down there. And the size, because you don't have a lasso tool, is that what? That's exactly what it is. And take your graph and recreate it down here so you can draw on it.
Boom, done.
Here's the conceptual part of what we're going to do. What you're going to do is you're going to split it up into 3 chunks. Okay. Now there's some names, and this abbreviation is what the textbook calls them. We're going to split it up into 3 pieces. We're calculating it manually here, so we don't want to split it up into more than that. I would like to show you eventually this. Now, this is a printout, so I can't just copy that, and the reason I don't have it open already is because I don't want to type that whole thing in. I actually do have something here for you. Hopefully that's this. This is what we're going to do here. We're going to, actually, it's better to do it by hand first and then see the technology, is it not? We could approximate the area here several different ways. We could decide that we're going to draw some rectangles. We're going to use it with rectangles. We could draw this one where they touch the curve on the left side. As in, we could say, let's draw a rectangle like that. We're going to split it up into 3 subintervals, like from there and there, 3 intervals. I don't want to do more than that because we're calculating it by hand, right? And you could say, I want to draw the rectangle so it touches on the left side of the subinterval. You know what a subinterval is, right? You know what the prefix sub does? Smaller, beneath, right? Submarine, below the water. A subcommittee would be a smaller committee within that or below that committee. And the third one is going to be right here. You could do that. That would be the left sum, where they're all touching on the left side of the interval. Before we calculate it, I want to draw for you the right one. The right one would be if you had it touch on the right side of each interval. Does that make sense? Okay, there's the right-hand sum. That doesn't approximate it very well, right? But where we're going with this is we're going to increase the number of subintervals using calculus, right? And limits. We're going to increase the number of intervals, and if I was to split it into 6 subintervals here, that would be a better approximation, wouldn't it? I think we have to pause and go. Okay, whoops, we have to recreate that for the video. There's the left sum. There's the right sum. How does the left sum approximate that area under the curve? Because what we're looking for is this actual area, right? We want that actual area. It happens to be, do I have it visible here anywhere? Yes, 33.6. Okay? Your guess was so close. How does that, what are you saying? What are you suggesting there? The midpoint sum for most things is going to be the best approximation. Okay? The midpoint sum is going to be the best. It depends. Well, the trapezoid is going to be pretty good, right? There's trapezoid. But the thing is, you could average the left and right. You could do all kinds of crazy things. But it's not going to matter once we start increasing the number here. Okay, so you notice this down here. This is the number of subintervals. So let's start with the midpoint sum here. I don't actually have it displaying what that sum is, but that's okay. If I increase the number of subintervals, what's going to happen with how well this approximates the area? It's going to get more and more accurate, right?
And beyond.
Like you can't even tell anymore, right? What about if I started, which one did I start with there? 10 minutes. And we have to quit on a high note? Is that what you're saying?